Hey, this is Mel, and this lecture is on greenhouse gases and the greenhouse effect. Before we get into the greenhouse stuff, we're going to talk a little bit about light. And one of the ideas in light is that light travels in waves. So there's several things in physics that travel as waves. So for example, we have sound waves, right? Earthquake waves. So energy can propagate as waves sometimes, and light is one of those things. So if you think about what a wave would look like, so I'm just going to draw some waves here. So now, when we get into waves in physics, there's some terminology that we use a lot. And one of them is something called wavelength. So if I had a bunch of waves here and I measured the distance between two consecutive parts on a wave, we call that the wavelength. So for example, trough to trough or crest to crest, that's literally the length of the wave. So light is made of waves that are so small that you can't see them. How small are they? So you can imagine if you took a meter stick and you divided it into 1,000,000 pieces, and then you take one of those pieces and you divide it into about 10 to 50 pieces and take one of those pieces, that's about the length of a wavelength of light. Okay, so these are submicroscopic waves, right? So we think of them and we draw them like this, but we can't actually see the waves themselves. Everything is way too microscopic. Okay, these waves, the way our eyes and brains are set up is what we perceive as color are actually different wavelengths of light. So when I see red light, that's a certain wavelength. When I say blue light, that's a different wavelength. The waves are physically different sizes, and our eyes and brains interpret that as a color. Okay, so what I'm going to do is we're going to draw if we could look at all of the waves from the sun, okay? So I'm going to make a graph here. On the x-axis are the waves. Shorter waves down here, longer waves over here. And on the y-axis is intensity. So we're going to look at all the light coming from the sun, and we're going to make a graph. If I did so, it would kind of look like this. So it's not symmetrical. There's a peak, and then there's this really long tail that actually goes on forever off the page. And if I drew it correctly, it would never come down to 0, but I kind of screwed up there a little bit. Okay, so let's explain kind of what this means. On this end, these are the waves coming from the sun that are really short. So I'm going to draw a little line kind of right here, because it turns out those waves are too short for our eyes to see. Then we start to get into waves that our eyes can see. And the shortest ones that we can see, our eyes interpret that as violet. So I'm just going to shade this kind of a violet purple color. And then eventually, as these waves get longer and longer, we interpret them to be more of a blue color. So I'm going to put some blue in here. And I'm not going to draw every color that we can see. I'm just kind of generalizing here. Okay? So then, as the waves get longer, they turn more and more of a green color. So I'm going to draw some green. Okay, and then as they get longer still, we start to get into the yellow, and then we get into some orange, which then turns more and more towards a red color. Okay, so something like this. So I'm going to put another little dashed line right there. So roughly, and this is really rough, but the idea is that over here we've got waves that are too short to see. Then we get into violet, then in the blues, greens, and then as the waves get longer and longer, we eventually see that as red, and eventually they are too long to see. Okay. Now the ones that are too long to see, we call those infrared. Sometimes we abbreviate this as IR. And the waves that are too short to see, we call those ultraviolet or UV. So UV is this entire region in here. Infrared is this entire region that goes off the page. Let's talk about UV first. So we've talked about UV in the past. We talked about the ozone layer and how the ozone layer blocks most, but not quite all, of the UV from hitting the surface, right? So UV light comes in, hits an ozone breaks apart, eventually gets back together, that releases heat to the stratosphere. Okay, so this little segment right here of UV is the UV that gets through. It's the UV that gets all the way to the surface. And the UV out here, this is the UV that's blocked by the ozone layer. Okay, so these shorter waves, it turns out, have more energy and they're more dangerous to us. So for us, things like X-rays and gamma rays, those are even shorter than this. Unfortunately, we have very few of those coming into the atmosphere from the sun. But those are very dangerous. And then the longer the wavelength is, it turns out the safer it is for us, for our bodies. Okay, so you don't want to get whacked with UV radiation. It's okay to get whacked with visible radiation, which is what we call this part in here. This is the part that we can see. Then we get out here to these longer wavelengths, and now we're back to waves that we can no longer see. Now the ones that are pretty close to red in here, we call this near infrared. And the ones that are way out here on this tail, we call these far infrared. So everything in the tail is infrared. Near is these guys, far, and it goes on and on and on this page. It goes on forever. Okay. Also, when you get far out on this tail, and it's kind of off the page, but I'm going to draw it here anyway, you get to some radiation that is, we can't see it, but we have another sense for it. You would call this heat. So if you were up to, let's say you walk up to a wall and the wall's hot, you have a sense that it's hot without actually having to touch it, right? Like you can sense it on your face, like you feel something. And out here we call this sensible heat. Not sensible because it has good sense, but sensible in that it's not, if you remember back some lectures, we talked about latent heat. Latent heat is heat that is hidden. Sensible heat is not hidden. You can touch it and feel it. So what we perceive as and what we talk about as sensible heat, that I touch something warm and it feels warm, that is actually, I'm feeling these waves way out here. Our eyes can't see them. Now it's worth pointing out that some animals can see other waves that we cannot, right? So we can't see near infrared right here. But snakes, for example, pit vipers, they have this little pit on their head and it's a sensor and they can see things that are warm and they're kind of seeing, they don't really see this out here, but they kind of see the near infrared part of that. A lot of insects can see UV out here, and so it helps them see different flowers. So our world is the visible, what we call the visible light world. These are the waves that we see, but we're surrounded with these other waves that we cannot. So with that, I'm going to then move to talk about what this has anything to do with greenhouse effect. What we do when we talk about the greenhouse effect is we take all of these waves and we group them into two categories. We basically say that everything from about here onward is called shortwave radiation. Okay, and so sometimes that means all the visible and UV. Sometimes people also include the near infrared, but it's the majority of this hump. That's the shortwave radiation. And everything to the right of this is long wave radiation. So that is this long tail that, again, it's much longer than I'm showing here. Goes off the page. So all the waves to the right of this we call long wave radiation. All the waves to the left of this we call short wave radiation. Okay, so we're going to talk about short wave radiation, long wave radiation, and just keep in mind when you hear short wave, it's the stuff you see with the UV. When you see long wave radiation, it's these really long waves that you can't see, but you might be able to feel as sensible heat. So one of the things that happens on Earth is that shortwave radiation comes in from the sun, and the Earth absorbs that and turns it into long wave radiation. Okay, so the way I would draw that is, so here's the surface, here's the sun, and mostly what comes in from the sun is shortwave radiation. That's the big hump of radiation we just drew. And it comes down and it goes through space unaffected, goes through the atmosphere mostly unaffected, hits the ground. And the ground absorbs this. And then the ground turns it into long wave radiation. And so coming off of the ground, beaming back into space, is long wave radiation. So this is the long wave. This is the short wave. Okay, so remember, back from the previous diagram, short wave, that's all mostly the visible plus a little bit on each side. What's coming off the Earth is the stuff way out here, including the heat that you can feel. So you can kind of think of the Earth as converting one type of radiation to the other. We see visible light, it comes in, it hits the ground, turns into heat that you can feel. So here's an illustration. Sun's out, turn you back to the sun, your back gets warm. Why? It's not heat coming from the sun. It's shortwave radiation coming from the sun. Your back absorbs that, turns it into long wave, and then you can sense it. So objects that are in the sunlight take that shortwave radiation, convert it to long wave radiation. Now on the Earth, this long wave radiation is beaming back out into space. Okay, so if you have any object floating out in space, Earth, the moon, whatever, it absorbs the short wave, beams the long wave back. So if you're floating around out in space and you had a thermometer, you could point it at the Earth, you would measure this coming off of it. So the Earth is like beaming this long wave radiation out in space, kind of like how the sun beams shortwave radiation out into space. Okay, so this is what's going on with the Earth. So with that, we're going to investigate what a greenhouse gas is and what the greenhouse effect is and all that. So this is another one of the PhET simulations. It's called the greenhouse effect. And what we have here is a box, and I can put a different kind of molecule in the box. So nitrogen, oxygen, water, CO2, whatever. And I've got a flashlight that can shoot either shortwave radiation or long wave radiation. Now what they're calling it here is they're calling it infrared, so that's our long wave radiation. And I can turn on the slider and it starts shooting what we call photons, little packets of light that are either So what they're calling infrared, we just called long wave. So these are long wave, this is little packets of long wave radiation. Or I can switch it to the visible light, which is the short wave radiation, okay? And it shows, what it's showing here is that the photons are just passing right through my oxygen molecule and nothing's happening. And I can switch this to nitrogen, and again, no matter what I do, the different types of light just go right through. So far, nothing really interesting is happening. What's our atmosphere made out of? Roughly 80% nitrogen, 20% oxygen. And so when I put these molecules in there, nothing happens, right? Okay, so let's say I change this though, and I'm going to put in a water molecule. Okay, so I got water molecules, and so just to remind you, there's the two the two hydrogens on one side, and it kind of has that Mickey Mouse head shape we talked about in the past. So if I change this to shoot long wave radiation at it, I'll notice that finally something different starts happening. And once in a while, the water molecule absorbs one of those photons of long wave radiation. It gets excited, it wiggles, and then it shoots it off in some random direction. Okay, so as I sit here and watch this, if I was standing behind this flashlight doing this, once in a while, one of those red photons of long wave radiation would come back towards me. Now, we just said that long wave radiation includes sensible heat, which you can feel, right? So if you can imagine me shooting these little photons of long wave radiation at this water molecule, and occasionally one of them comes back towards me, like that one right there, then my experience as the guy behind the flashlight is I feel the warmth of that little photon coming back. Okay, so I'm going to make a bunch of them. Let's build an atmosphere. I'm going to put a bunch of waters out here, and I'm going to turn on my flashlight. Come here. And I start spraying this box of water molecules with photons of long wave radiation. And as I stand back here, I'll notice that occasionally some of them come back towards me. Okay, this is what we call the greenhouse effect. And water is a greenhouse gas because it does this. Not all gases do this. So I just illustrated this, but if I had a bunch of, let me take my waters back, come on, and I'm going to increase I got a bunch of oxygens, and I got a bunch of nitrogens, and now I will shoot those guys, and that the long wave radiation just passes right through, and you see these molecules just don't care. Nothing's happening. So none of those photons are getting reflected back towards me at any point. On the other hand, if I went to, let's get rid of my nitrogen, let's get rid of my oxygen, come on, and I could put in some CO2. So CO2 is another one of these molecules that acts as a greenhouse gas. You can see they get excited occasionally, and they shoot off a photon in some random direction, and that random direction might be back towards where I am. Methane. Methane is a CH4, has carbon with 4 hydrogens. So I'm going to go back here and make a atmosphere with methane. And so as I shoot the methane with the long wave radiation, you can see it also gets partly absorbed and reflects back towards me. It's also worth pointing out that if I put the flashlight on visible, so shortwave radiation, and I fill up the atmosphere with nitrogen and oxygen, that the shortwave radiation goes through the atmosphere completely unaffected. And if I put in greenhouse gases, so methane, CO2, water, that nothing is affected here. In other words, the shortwave radiation pretty much just goes right through the atmosphere. So it's coming from the sun, goes through the atmosphere, does not interact with hardly any gases. It's the long wave radiation that is interacting with the greenhouse gases. Okay, so oxygen, nitrogen, no interaction whatsoever with anything. The greenhouse gases, and so far we've seen CO2, water, and methane, do interact with the long wave radiation. Okay, so let's return back to this diagram that we just drew. And what we have drawn here is a scenario on a planet that has no greenhouse gases. So let's just say our atmosphere was oxygen, nitrogen. We have no greenhouse gases, or maybe no atmosphere at all. Shortwave radiation comes in, hits the ground, goes back out into space as longwave radiation. If the Earth had no greenhouse gases whatsoever, just oxygen, nitrogen, then our average temperature of the entire planet is somewhere around 4 degrees Fahrenheit. Okay, so this takes into, this is the whole Earth now. So it's the poles, it's the equator, it's the summers, it's the winters, the days, it's the nights, all thrown together. You get a number about 4 degrees Fahrenheit. So pretty close to 0 Fahrenheit. What would the Earth be like? If the average temperature is about 0, that means you're looking at an Earth that is essentially entirely frozen. The oceans would probably be frozen completely over, right? So that's what it would be like if we had no greenhouse gases. Okay, so now let's take this scenario and let's add one thing. What if we had a planet that had clouds? Okay, so we're just going to do that first. So redraw. Okay, so in this scenario, we have clouds. And so I'm going to draw these as some physical objects in the sky. Okay, and what happens? Well, shortwave radiation still comes down from the sun as before, which I'm drawing as blue. And clouds will reflect some of that shortwave radiation back out into space. Okay, so that's a possibility. And one of the things that we'll do is that will help cool it down during the day, right? So cloudy day, usually not as hot. It's because we are reflecting some of that shortwave radiation back out into space. But the shortwave, some of it still gets to the ground and still turns into long wave. And long wave then heads out into space, just like before. But the difference now is that we have some clouds. So some of it will make it all the way out to space, right? That one makes it out to space. But maybe this one hits this cloud. And some of it goes through, but some of it reflects back. This one hits the cloud. Some of it goes through, some of it reflects back. Okay? So if you are an observer on the ground down here, so we're saying this is the same planet as before. So the planet before had no greenhouse gases. It was 0 degrees. The person on that previous planet could feel the warmth coming up from the surface. This person also feels the warmth coming up from the surface, but now there's a little portion of it that's coming down from above. So in other words, this little reflection may come down and hit you, and you now feel like there's a little bit of warmth coming up from those clouds. So the presence of clouds, and so we've kind of skipped greenhouse gases here for a little bit, but the presence of clouds means that you will have cooler days, but you'll have warmer nights. Okay, so generally speaking, if it's especially in the winter, if it's cloudy at night, it's going to be much warmer at night than it is if it's clear at night, because a lot of this long wave radiation that's coming up is reflecting off of these clouds and coming back towards you. And so just to be clear, make sure what I'm doing here, all my red ones, those are all long wave radiation going out towards space. So the big picture here is everything is the same as before, except these clouds are going to cause some reflections. Some reflections of shortwave back out into space, makes things cooler. Some reflection of long wave radiation coming back down makes things warmer. So the big picture is a cloudy planet, going to be warmer at night, probably cooler during the day. Okay, so now here's our third scenario. Now we have an atmosphere that has some greenhouse gases, and I've drawn some greenhouse gases here. I've not drawn in oxygen and nitrogen because, as we've just kind of demonstrated, they have nothing to do with either long wave or short wave radiation. So I'm not drawing them. I just threw in some greenhouse gases. We've got some methane, we've got some water, we got some CO2. Okay, so what happens in this scenario? Shortwave radiation still comes in from the sun. So here's my shortwave coming in. And long wave radiation heads out to space from the surface. And as it goes out, some of it goes out and goes all the way until it it goes all the way out into space. And sometimes it will interact with one of these greenhouse gases. So back to the animation where the greenhouse gas got excited and wiggled and then shot that photon in a random direction. Well, that's what's happening here. This outgoing, there's my long wave, coming out, is going to interact with this CO2. CO2 gets excited, wiggles, shoots out a photon in some random direction. Okay? And this is happening all throughout here, where some of these interactions are sending the long wave radiation in various random directions. I'm just going to draw a few of them because it takes forever. So what I'm trying to draw here is that there's all these interactions occurring with greenhouse gases. Now, eventually, this long wave radiation will make it out to space, right? It'll bounce back and forth between one molecule and what have you. Eventually, it'll get out. But before it gets out, the person on the ground down here is experiencing these photons of long wave radiation coming back down out of the sky. Now before, we say they're coming down reflecting off a cloud. Well, in this case we have no clouds, but they're still coming back down. They're reflecting off of these invisible gases, these greenhouse gases. So if this one, for example, comes down to the ground and hits this person, and this person feels warmer, well, eventually, if we just think about where that ultimately goes, it'll eventually head back out into space, and it may reflect back and forth several times, but it'll eventually get out. It'll eventually go out into space. But you can think of this as like we're recycling some of these photons of long wave radiation. It was all headed to space. It got intercepted on the way there, got rerouted back down towards the surface, some of it, and then as it hits the surface, then it's headed back out to space for a second or third or fourth or fifth time. So this is what we mean by greenhouse effect. The greenhouse effect means we have these molecules that has this property of being able to absorb long wave radiation, redirect it in a random direction. That random direction could be back down towards the surface, in which case it makes the surface warmer than it initially was going to be. That's the greenhouse effect. And because of the greenhouse effect, the worldwide average temperature is about 54 degrees. Okay? And that's lucky for us because that's above freezing. So we could not survive without the greenhouse effect. So prior, we said that without the greenhouse effect, the entire Earth is below freezing, okay? We have to have the greenhouse effect to survive on this planet. It just turns out that in the last 100-ish years or so, we as humans have been adding too much of a good thing to the planet and to the atmosphere, and we are increasing this greenhouse effect. So as we get into climate change, what I want you to keep clear is you got to have the greenhouse effect. You got to have it, otherwise we die, right? But we've got a little too much of it now. And so things are warming up because we are reflecting more of those long wave photons back towards the surface that are supposed to be here. Okay, we're going to return to that PhET animation, and we were looking at this tab called photon absorption, and now we're going to go over to greenhouse effect. And what they're trying to show, they're trying to animate basically what we just drew. They're using yellow to represent shortwave radiation from the sun. So these little yellow photons, that's the visible light plus the UV, maybe some near infrared coming down. And the red represents the long wave radiation going back out into space. Okay, so this is what we drew as arrows. I used the color blue, they're using the color yellow, but there's photons coming in, there's photons going out. No greenhouse gases. And it shows that the worldwide temperature is about, now in this case looks like it's about -2, pretty close to 0 degrees Fahrenheit, right? So the world is frozen. Now, what I can do with this is I can put in greenhouse gases and watch how things change. So right now, this entire time I've had this, it says greenhouse gas concentration, I've had it on none. I'm going to turn it up to somewhere in the middle here. And what I want you to do is notice how the red ones change their behavior. You'll notice if you watch one for a while, it'll suddenly change direction. That's where it's interacting with a greenhouse gas molecule. And kind of like I drew with arrows reflecting, these little photons of long wave radiation are headed out to space, but before they get there, they often get intercepted, redirected, and a lot of them come back down towards the surface. So what that means is the surface is getting warmer. And you can see the temperature has been rising here. Okay, so this is the greenhouse effect, and they're not showing you the molecules. I drew those in on our last paper, but it's animating the effect that the greenhouse effect produces. I could also just turn it all the way up. So I'm going to crank it all the way up, greenhouse gas concentrations all the way to where it says lots. And you'll see a lot more interactions with the red photons. You see a lot of them bouncing around, meaning that they're interacting with greenhouse gas molecules coming back towards the surface. And we see that that surface temperature is now increasing. It looks like it's getting up to over 70 degrees. Now remember what this means. This is not 70 degrees. I mean, that doesn't sound bad at all. That's a worldwide global average. So it's also including the poles and the days and nights and the winters and everything, right? So worldwide, the entire temperature is increasing if I increase the greenhouse gas concentrations. So we're going to talk about some of these different greenhouse gases, but before we do that, we're going to talk a little bit about some of the gases we've talked about so far in class. And so early on in the semester, we talked about how the atmosphere is mostly oxygen and nitrogen, a little bit of argon, a little bit of CO2, a little bit of water vapor, and then up in the stratosphere, a little bit of ozone, right? So these are all naturally occurring. Then we did a section on air pollution. We talked about gases. Some of these are human created. Some of these are naturally occurring, but humans add to that. So things like carbon monoxide, SO2, NOx, and all those things. So that was part of our air pollution unit. Okay, so now we have a third category of gases that we're calling greenhouse gases. Okay, and of the greenhouse gases, we can subdivide them into two categories. One is naturally occurring greenhouse gases that we as humans are adding to. And then there's a second category of greenhouse gases that we as humans have just created. They're synthetic molecules. Okay, so before we get too further in on this, we're going to really be focusing on this group right here, CO2, CH4, and N2O. And we're not going to really talk about water vapor, even though water vapor is the most abundant greenhouse gas in the atmosphere. So why would we not talk about this? Well, if you go back to when we talked about humidity, we said that the amount of water vapor in the atmosphere is controlled strongly by temperature. So warm air has a higher possible maximum mixing ratio, right? And if you cool the air down, remember we hit the dew point, we condense water out. So water vapor cannot stay in the atmosphere if the atmosphere is too cold, right? So if we all as humans got together and started adding water vapor to the atmosphere on purpose, let's say, it won't stay in the atmosphere more than maybe a few days before it drifts off into someplace cold, condenses out, and it gets removed from the atmosphere. The greenhouse gases that we're interested in are the ones that are not being removed in a short time, okay? So that's why we're not really talking about water vapor, even though water vapor is a pretty significant greenhouse gas. Okay, so it turns out the strengths of greenhouse gases are not all the same. And if you think back to the animation where I was shooting molecules with a little gun, occasionally a molecule got excited and absorbed that photon of radiation and then re-emitted it, okay? Well, some molecules absorb radiation much easier than others. They are much more efficient at being greenhouse gases. And so we have this system called global warming potential, or GWP. And what we say is that greenhouse gases, so on the left, these are all greenhouse gases. And by the way, if you're one of my students, what I'm showing you here are part of what we used to have handouts in my face-to-face class. So this is all in Learn, so you can find this document in some of the future slides too. So what we say is that CO2 has a GWP of 1. Okay, that's arbitrary. So methane, CH4, has a GWP of 25. So what that means is CH4 per molecule is 25 times as powerful of a greenhouse gas as CO2. So if I had 1 molecule of CH4, it's worth 25 molecules of CO2. Or if I take nitrous oxide, N2O, it has a global warming potential of 298. So 1 molecule of nitrous oxide is worth 298 molecules of CO2. So greenhouse gases all have very different strengths. And what we want to do here is we want to be able to compare different sources to see which emissions are actually affecting the greenhouse effect more. And so if I go back a slide, these were the naturally occurring ones, and we as humans add them. That's these 3. And then all these are synthetic. Okay, we as humans make them, they don't occur in nature. Notice though how strong some of these are. This one has a GWP of 14,800. So 1 single molecule of HFC23 is worth about 15,000 CO2 molecules. Also notice that they are up in the atmosphere sometimes for a very long time. I mean, look at this, CF4 has an atmospheric lifetime of 50,000 years, meaning that once it gets into the atmosphere, there's no natural processes that break this down. It's going to be up there a very, very long time. Okay, so what we want to do is let's imagine a scenario where we've got 3 different greenhouse gas emitters, like say 3 different factories, but they're not all emitting the same gas. You've got one emitting CO2, you got one emitting methane, you got one emitting nitrous oxide, and you want to know who's actually making the biggest contribution to the greenhouse effect. So in order to do this, we have to convert all those gases to what we're going to call CO2 equivalent. The analogy is like money. If I had something in dollars, so I have some item that's worth a certain amount in dollars, I have another item that's worth a certain amount of pesos, I got a third item that's worth a certain number of euros, and my question is, well, which one's the most expensive? I won't know till I convert them all to the same currency. What we're doing here is we're going to convert all the gases to the same currency of CO2. And we're going to use the global warming potential to do this. Okay, I'm going to work through a problem. So, let's say we have a cement plant. And the cement plant is emitting 1,200 kilograms of CO2 per day. Okay? And then we have a gas plant that processes natural gas. We'll talk more about this later. And it is emitting 150 kilograms of methane per day. Okay? Then we have a fertilizer plant. And let's say it is emitting 25 kilograms of nitrous oxide per day. All right, so the question is, if this is the scenario, let me refocus here, then if I compare these three, who is contributing the most to the greenhouse effect? Okay, so what we said a few minutes ago is that we need the greenhouse effect to survive on the planet, but as humans we're adding more to it. Here we have three different outfits that are emitting greenhouse gases, but what we want to know is who's adding the most. Okay, who's making the biggest contribution to the greenhouse effect through greenhouse gas emissions. So in order to do this, we're going to convert everything to CO2. Now, cement plant, it's already in CO2, so I don't have to do anything, okay? No work, okay? That's done. So what I do have to do is take the gas plant and I want to convert. I want to say, okay, if it is emitting 150 kilograms of CH4, what is the equivalent amount of CO2 that would be? We're converting currency here, okay? So I'm going to take 150, this is CH4, and what I'm going to do is multiply that number times the global warming potential. So the global warming potential of methane, CH4, is 25. 1 molecule of CH4 is worth 25 CO2s. All right, so I multiply that by 25. Okay, so I'm going to take 150 times 25. I get 3,750 kilograms of CO2 equivalent. Okay, so that 150 kilograms of CH4 is the same amount of global warming potential as 3,750 kilograms of CO2. All right, let's do the fertilizer plant. So I've got 25 kilograms of N2O, nitrous oxide, and I look up the GWP of N2O, it's 298. So multiply by 298. 25 times 298, I get 7,450 kilograms of CO2 equivalent. Okay, sometimes we get really tired of writing out the word equivalent. So what you'll see instead is CO2 EQ, and sometimes in parentheses. That means equivalent CO2. All right, so we've converted currencies. Our cement plant is 1,200 kilograms of CO2. Our gas plant is equivalent to 3,750 kilograms of CO2. And our fertilizer plant is equivalent to 7,450 kilograms of CO2. So who's making the biggest contribution? The fertilizer plant, okay? So even though it was the smallest overall amount in terms of mass of gases, these nitrous oxide gives such a potent greenhouse effect. Overall, when you multiply the whole thing out times the global warming potential, you find out that it actually makes the biggest contribution. So if you're one of my students, you'll have a couple of these problems you'll have to work out this week. Okay, so here's a breakdown of the major greenhouse gases that are emitted in the United States, and they've been converted to CO2 equivalent. So it says percentages based on MMT, million megaton. That's just a gigantic number. Don't worry too much about that. CO2 equivalent. Okay, so what this is showing is that 82% of all the greenhouse gas emissions that we produce in the United States is CO2. Okay, and if you convert the other ones to CO2 equivalent, so there's methane and there's nitrous oxide, and then here's a whole bunch of the other ones. What you see is that even though these are a stronger greenhouse gas, as a nation, we emit CO2 by such a greater volume that this is the greenhouse gas that we typically focus on when we're talking about global warming issues. The CO2 is the number one gas that we're worried about. That doesn't mean we don't worry about these others. We do, because they do have a greenhouse effect. But CO2 is by far the biggest one that we worry about. So here's another way to look at those same numbers over time. So the blue is how much CO2 we've emitted each year. Then the red is the methane, green is nitrous oxide, and then purple is sort of a whole bunch of other ones all thrown together. As time has gone on, you'll see there's kind of this overall trend from early 1990s to the mid-2000s, where every year as a country we're emitting more and more greenhouse gases. And again, these are you can't really even wrap your mind around these numbers. So this is 7,000 million megatons. So you have to basically add 12 zeros onto the ends of these numbers, but don't worry about that. It's just a meaningless, gigantic number to you. Notice what happens here. 2008, things go downhill a little bit. So the world economy slowed down. We stopped buying things. We stopped building things. We stopped burning so much fuel. And we see that there's a little drop off here. But as years go by, you can see that the trends are pretty similar, right? That as a nation, we tend to emit mostly CO2 and then methane and nitrous oxide as our greenhouse gases. So we're going to talk about what we do to generate some of these greenhouse gases. So again, this is part of the figures that are on this handout that I've got on Learn if you're in my class. So sources of CO2 emissions, again, in this million megaton CO2 equivalent. Okay, fossil fuel combustion. Now, before I talk about that, look at some of the ones below here. Non-energy use of fuels, iron and steel production, natural gas systems, cement production, and down here on the x-axis are numbers in this million megaton CO2. So 25, 50, 75, but this very first one is so long, it would be off the page on through next several pages, and it would end over here at 5,000. So what they did is they put a little dash right here to show that this is not continuous. That the rest of these bars, this is 150, that's the scale. So this moves on for, a dozen pages later if this was all to scale. Okay, so that number right there, that 5,050, that is a so much larger number than all of these. So what this is saying is that the number one source of CO2 is burning fossil fuels. That's the number one thing we do more than anything else. Then we've got some of these other things. You probably have at least heard about some of these things. So when we make cement, that adds CO2 to the air. When we make iron and steel, adds CO2 to the air. All these things add some CO2 to the air. But that very first one, that fossil fuel combustion, boy, that is by far, the number one thing that we do. So in this table, we are breaking down the CO2 further. So we said that this number right here, this 5,050, is, so 5,050 million megatons of CO2 were produced in 2015 in the United States for burning fossil fuels. Okay, that's what there's that number. We can break that down further. Of that 5,050 million megatons, 1,900 was for generating electricity. 1,736 was for transportation. 805 was for residential. Industrial. 319 was for residential. Now, the reason I'm bringing this up is that most people don't realize that when we talk about burning fossil fuels, okay, we're generating CO2 from burning fossil fuels. The number one thing we burn fossil fuels to do in this country is not to drive cars. The number one thing is this one, generating electricity. So we produce more CO2 from generating electricity by burning fossil fuels than we do, say, burning fossil fuels in our cars. Cars, ships, everything, airplanes, etc., that's transportation. That's number two. So number one, generating electricity. Number two, transportation. And then it breaks down further from there. When we get to methane, the number one source of methane in this country is something called enteric fermentation. What is enteric fermentation? Fancy way of saying cow farts. So cows, they eat grass, grass goes down, they got this weird four-stomach system, and so you heard about cows chewing their cud, right? So they chew this grass, it goes down, and eventually it comes back up, and they chew it for a while, and it goes back down, and there's bacteria down there, and the bacteria produce methane, and the methane sometimes comes out the front end, sometimes comes out the back end of the cow, but cows produce a lot of methane. As a country, we really like our hamburgers, so we have a lot of cows, and cows produce a lot of methane. That's enteric fermentation. That's the number one source of methane in our country. Number two is natural gas. So we're going to talk about this in a future lecture, but when we extract natural gas out of the ground, some of it gets into the atmosphere. Number three is landfills. So this is where all your garbage goes. They just throw it in a big hole in the ground and cover it. Bacteria decay that garbage, and then that produces methane. Manure management might be a career option if college isn't working out for you. Coal mining, petroleum systems, wastewater treatment, that's where all your sewer goes. Methane's produced through that. So there's a bunch of them here. And here's a breakdown of nitrous oxide. And number one on the list is agricultural soil management. So this is another one of those graphs that they had to break because it's so much bigger than all the other ones. So number one by far is agricultural soil management. What does that mean? So plants need nitrogen, but they can't take nitrogen out of the air. They have to take it out of the soil. But there's a limited amount of nitrogen in the soil. So what humans have done is they figured out how to add nitrogen to the soil. We make something called synthetic fertilizer. And they look like these little BBs. You throw them into the soil, and they break down and they produce nitrogen that the plants can absorb. Well, one of the byproducts of that is some of that produces nitrous oxide, which then goes into the atmosphere. Okay, so that's your number one here by far. Number two, stationary combustion. That's something that's burning but not moving, like it could be an engine that's not moving anywhere. It could be a fire. Manure management again. Mobile combustion. Okay, so now you got an engine that's on the move. Wastewater treatment again, so on down the line. So the number one, though, by far is agricultural soil management. So if we think about all of the variety of sources, that is the greenhouse gases we're putting into the atmosphere, and sinks, these are things that remove greenhouse gases from the atmosphere, it kind of looks like this. So this is on the y-axis, it says million megatons of CO2 equivalent, right? So we're taking all the different greenhouse gases, converting all of them to CO2 equivalent, throwing it all together, and looking at what we got as a country. So the blue is energy, okay? So most of the greenhouse gases are from this energy sector. So that's electricity, that's transportation. Energy is a lot of things there. Then the red is agriculture. Then the green is industrial processes of some kind. This little blue here is waste, so that's mostly us throwing things away. And then this little tiny one, it says LULUCF, which stands for land use change, and forestry. Okay, and we'll talk more about this in a little later lecture. Okay, so as time has gone on, as the economy has grown, you can see overall the amount of greenhouse gases has gone up and up and up, like we saw in the earlier slide. Then the economy kind of crashes in 2008 and drops down again. But by and large, the number one thing that we do as humans to produce greenhouse gases is generating energy of some kind, right? Either electricity or our cars or what have you. Also notice this purple, which is negative. Okay, this is what we call a sink. So what that means is these are processes that take CO2 or other greenhouse gases out of the air and remove them. Well, what would that be? So imagine really intensive farming. If you plant a lot of plants in a tiny area, then they're going to pull down CO2 out of the atmosphere, and they'll actually offset some of the CO2 that we've been putting into the atmosphere. So that's what we mean as a sink. That's this purple.